Hi there, we're continuing our chemistry lesson on chemical energy changes, and we're now shifting to Le Chatelier's principle, and we've already looked at what is the equilibrium position, and that's going to be important for this lesson. What we said the equilibrium position is that when reaction in equilibrium has a position for the equilibrium. Either the position, so here's my reaction, A plus B and C plus D, and then I like to just use lowercase letters in front of the compounds to represent the amount of moles that react in ratio with one another. Okay, so a reaction in equilibrium is first of all a reaction in a closed conditions or closed system. It's a reversible reaction. The reason why we have equilibrium is because the rate at which the products are produced and the rate at which the products produce reactants are the same, and that is when we reach equilibrium. Now in this equilibrium we can either have our equilibrium to the left or to the right. Okay, so wherever the percentage lies, so for example, if this was my closed container, okay, and I have in my closed container, this part represents the percentage of reactants, and that part represents the percentage of my products. You can see that the position of equilibrium, in this case, there are more reactants than there are products, so the position of equilibrium is to the left. Okay, to the left. Now it does look like the position is to the right. I must say that initially confused me as well, because it looks like the position is to the right, but that's not what we mean. We mean that there are more reactants than products, so the position is to the left. Okay, now from there, Chatelier's principle is a principle relating to this position of equilibrium. How can we move it? I don't want there to be more reactants than products. I want more products. I'm trying to produce this by any rate. Okay, so what can I do to change that? Now Le Chatelier's principle states the following: that if a stress is added to a closed system in equilibrium, the equilibrium will shift in the direction that will relieve the applied stress. Now, first off, it might sound a little bit, I have no idea what it is saying. How can the equilibrium shift, or what does it mean? But I suppose the first question we should ask is, what do we mean by a stress? Okay, what do we mean by stress, especially if I spell stress with two S's? Okay, what do we mean by stress? Okay, a stress is something that literally affects the equilibrium, and we will look at how what are the things that we can do to change the equilibrium. Now, the first thing that we might consider is temperature. Okay, temperature. Now we can ask, well, how does temperature affect the reaction rate, okay, or the equilibrium? Now we have to remember that the reason why temperature affects a reaction is because it adds energy into the system. Okay, now our question would be, which side will benefit from energy added to the system? Okay, so if we add energy to the system, we are obviously adding well, not obviously, we're actually adding a reactant. Okay, now which side of the equation needs temperature as a reactant? Well, there's two possibilities. We can have exothermic and endothermic reactions. Endothermic reactions. And if we have a reaction that is reversible, and the forward reaction is exothermic, then the reverse reaction will be endothermic. Okay, so here we will definitely also look at exothermic, means my forward reaction will have a enthalpy that is less than 0. Remember, the change in enthalpy tells me how much energy is needed for a reaction to occur, and when my enthalpy is less than 0, it means I have a negative answer, which negates what I'm saying. I don't need energy. Energy is expelled, exothermic. Okay, endothermic will have a positive enthalpy. This means that the reaction needs energy, so energy is absorbed in this reaction or added in this reaction. Okay, so when we have an exothermic reaction, we are saying that your reaction has heat as a product. Okay, so let's write it like this. Yeah, well, let's keep it heat is a product, while an endothermic reaction, heat is a reactant. Heat is a reactant. Okay, so I hope you understand what I mean by this. If I'm saying heat is a product, I mean among the products that is being produced, heat is also being produced. And if it's a reactant, among the things that I need for the reaction to occur, I need heat for the reaction to occur. So if I increase the temperature, I am definitely increasing something on to the left or to the right. Now if I increase temperature, it means I'm adding a reactant, either a reactant for the reverse reaction or a reactant for the forward reaction, and that places a stress on the system. So for example, in an exothermic reaction, I will have my product A plus B, forward and reverse reaction. Okay, so for exothermic reaction, I have C plus D plus heat. So if I were to add heat, in other words increase the temperature, I would be placing a stress. I would add stress on the left hand side of this reaction. Now if I add products in this case, I am favoring this direction of the reaction. Okay, so overall I'm increasing the reaction rate. Okay, all on both sides, all of the molecules have more energy because temperature is being increased, so both reaction rates are increasing, but the reaction rate that is being favored the most is the reaction rate in this direction, because by adding heat into this reaction, I am adding more of the products which want heat for their side to occur. So if they want this, it means they are more likely to produce more of these. Okay, I hope that makes sense. I really don't know how else to say it. Okay, so if I place a stress on the system on the left hand side, then what happens is the reaction tries to compensate for that stress by forcing the reaction to move in the other direction. Okay, that is if I have, this is the, if it was a exothermic reaction. So exothermic favors reverse. The exothermic favors the reverse reaction, okay, because exothermic means heat is a product, and if heat is a product, then by adding heat, we'll go in the opposite direction. We'll favor the creation of reactants. Okay, now I could also decrease temperature. So if in an exothermic reaction I wanted to produce more products, then obviously I should take away this heat. I should try and remove heat from the system, because by removing heat from the system, then unfortunately all the reaction rates are decreasing. Okay, so heat was increasing the reaction rate overall, okay, but now the percentage of products produced will increase, because by taking away the stress of heat, okay, I'm literally doing the opposite of changing the equilibrium to move to the left, because if I were adding heat, equilibrium will move to the left. So if I take away heat, equilibrium must move more to the right, okay, favoring the forward reaction. Okay, now obviously the complete opposite works for an endothermic reaction. If I have A plus B, endothermic means I need heat, I need to add heat for this reaction to occur, and then C plus D. Now if I increase temperature, if I add more heat, I am adding more reactants. More reactants means more likely successful collisions among the reactants, and therefore I will favor the forward. So by increasing heat for endothermic, okay, favors the forward reaction. Okay, again, if I take away heat, I'm removing the some of the reactants, which means that I'm doing the exact opposite, and I would favor the reverse reaction, which then means that more of the reactants will be produced in the reverse reaction, so the equilibrium will shift to the left. Okay, so in the next video, I'm going to stop this here. In the next video, I will look at some other changes we can make and their effect on the position of equilibrium. We'll see you there.